Hey, hi everyone, welcome to our event. This event is brought to you by DataTalksClub, which is a community of people who love data. We have weekly events, and today is one of such events. Although lately we didn't have them weekly, but that's the idea. We have these events, but if you want to check out all the events we have in our pipeline, you can go to this link. Right now it will be empty, but we will soon add a couple of more events, specifically the events about our upcoming free courses. So keep an eye on this. Then do not forget to subscribe to our YouTube channel. This way you will stay up to date with all our future streams. And last but not least, join our amazing Slack community where you can hang out with other data enthusiasts. During today's presentation, you can ask any question you want. There is a pinned link in the live chat, ask your questions, and we will be covering these questions after the presentation. I assume you will have like a Q&A slide, right? So
Yes.
this is, we'll cover all these things. Just a quick question for you, Florian. If there is a question that is relevant to what you show right now, would you like me to ask it as you go or wait till the end?
Actually, that would be so awesome if you would ask right away.
Okay, so I'll try
Because
to do this.
because if I think about myself like the next half an hour just talking to myself, it feels a bit weird. I need this feedback from the audience. So when the
Okay.
first question comes up, please ask right away.
Yeah, I will be keeping an eye on Slido. I will also keep an eye on the live chat. And if I have questions myself, I will also ask to make it less boring for you, Florian. So right now the floor is yours. So welcome, Florian. I'm really looking forward to the presentation you have prepared because we together recently made a demo of what Florian is working on. And that was so interesting. You will see this actually soon. This was so interesting that I asked Florian to make a presentation about that, make a webinar, and today we will see that. So thanks for joining us today, Florian.
Cool. Thanks for the introduction. So first I show you a bit about company I work at, in case you don't know. So I work at Jina AI. And the mission of this company is to own this search vertical. So rather than focusing on a single domain, we empower all domains that need search with good search foundation models and everything actually you need in creating search engines. And a lot of our technology is open source. So we were founded in 2020, headquarters in Berlin, 30 people. And then you can see these numbers of open source projects. We are a lot, so even more than people working here. So you have a rough number of what this means. So we were highly committed to open source and started in the early days. So we built up quite a large open source community over time. And please check out our repos if you want to learn more.
And don't forget to give them stars for all the projects because what they are doing is amazing. And I really love this kind of spirit when companies share a lot of things open source. Yeah, sorry for interrupting you,
Yes.
but
So
please give them
it's a
stars.
very valid point. Give us a star. I agree. And then, yeah, you can see it's not even possible to name this number. So many tokens we process every day, and we have model downloads and so on. So we became quite relevant, but it was also a hard fight because it's not so easy in open source community to get in this position. So here are our investors, in case someone is interested, and maybe you recognize some of these logos. These are partners we work with. And then I quickly just explain the three products we have. They are all open source, just that you get an overview. What does it even mean to be a search vertical? So first we have Reader. This is our program that allows users to get website content, but not just the HTML. That would be easy, just downloading the HTML of a website. No, it converts it to a format that is LLM friendly. So a large language model can read it easier because an HTML is full of all these tags and CSS and everything. So we trained models that allow to input an HTML file and get some markdown format that is easy to understand by large language models. And this is, you can consider it as the very first step of a search system, because at some point you need to read data from the wild, and getting it into some format all your downstream processes will understand. So there's this component. And then embedding models is a bit more complicated, but so far I can just say it's for semantic search. So instead of exact keyword matching, it's capturing the semantic of the documents and empowering the search with fuzzy matching, kind of. And then re-ranker is even more sophisticated AI model. When retrieving some documents, you can afterwards use that model to re-rank it. It's even more powerful than the embedding models. It can even better judge if a document matches certain query, but it also is a bit more costly. So you would just use it on the top 100 documents you retrieved and not on all the million of documents. But yeah, just you don't have to understand everything in detail, but I just wanted to show you a bit of our offering. And today's presentation will be actually about how we can build an agentic search flow. Because this is something I didn't list in our product offering so far, but this is coming up right now. So it's a very fresh content you see. Okay, I already sketched it a bit. So we came from keyword search. Keyword search is our search algorithms where the user types something into search query and they have to know exactly what they're looking for, because the target documents only match in case there is an exact string matching on what the user is typing. I will explain this a bit more in detail in the following slide. And then there is a semantic search where the user can describe a bit more abstract what they're looking for and then get the relevant documents based on this description. And it doesn't even have to match exactly like in the keyword search. It can have like a very different way of describing the same thing, but it's still considered a match. I will also explain this. And then I will need to explain these base concepts, because agentic search is then now the next level of improvement of search engines, where you have as user a bit of a hands-off experience, because there, instead of you trying different search terms and crawling websites and so on, an agent is doing this for you. So we start with keyword search and what are the advantages and what are the disadvantages. So keyword search is, as I said before, exact matching. You can even make this a bit more like fuzzy matching when you maintain a list of synonyms in your search engine. So then you can, when a user searches for a certain string, then you can check in your synonyms dictionary and then find all the synonyms and then extend the search query from the user to also search for the synonyms. But you can already imagine this is quite limited, because it needs a lot of effort maintaining this list of synonyms. And it's for certain scenarios, it's just exploding, because you cannot write down all possible ways the user could send a request. And then you even have to think about handling misspelling. So this is where you also can see where all the synonyms you would have to write are just exploding, because there's almost infinite way of how you can misspell something. Then keyword searches, we're also using wildcards. This allows also a bit more fuzzy matching, but it's limited. And I show you an example where it's working and where it is limited. So let's look at this example. Best budget smartphones 2024. And so you can see, like, here is a document that is matching, and it's a good document because it contains all the information. So presumably in this document, there's a list of all the best smartphones. And it is matching because it finds the exact words. So budget is found here, best is found here, and smartphones, and 24. So this worked, but it's also a bit lucky. The document where the information is contained in contains the exact same words. We cannot always assume. And here you see a so-called false negative. So it's considered not a match, but it is actually a document that there would be a perfect match, because even it says, instead of budget, it says affordable, and then instead of smartphones, it writes mobile phones, and it's not the best, but the perfect ones. And it's this year, or should be last year, and it's 2024. It's still considered by the search engine as like a very bad document because it doesn't have any overlap with the query. And based on these observations, people came up with the next paradigm of search. It's called semantic search. And it matches documents based on the meaning and not just on the exact string. And let's look at this query. So purchase this Samsung, and then it has certain version number. The good thing now is still, like, it matches these documents, even there is purchase, and it's here in the document it's buy. It also matches exact things, because like distance from Samsung to Samsung is still like 0 for the semantic search model. But what it has now problems with is, version number, which is also, but what it has problems with is to capture the semantic meaning between these two version numbers. So for the model, if it's not very specifically trained on only considering version numbers and so on, this is almost the same. So the semantic search, the embedding model, will look at this and think like, yeah, it's the same. It's like, okay, there are some different numbers, but semantically, it's very similar. And at this point, we wish we would actually go back to keyword search and have an exact matching, because this is not the same for us. We want to have this smartphone and not that one. So there is something called hybrid search, which combines both. It allows to specify parts that should perfectly match and parts that should have some fuzzy matching. So there are a lot of vector databases that allow both. There's two methods of pre-filtering, post-filtering. It's basically, you have one part of your query specifying a hard filter condition on all the documents. Certain attribute of the document has to be true, has to be false. Version number has to match, ID has to match, and so on. And there is this fuzzy part, this semantic part of the query, where you can define that it's defines certain meaning of the document, and then it has to match the meaning. But here, still, we can see, yeah, this query comparison, Google Cloud and AWS pricing. Of course, the document matches. Here's an overview of all GPC and AWS offerings and their costs. This document perfectly matches. But I can tell you, in reality, it doesn't exist. So, and if it exists, it's not up to date. So yeah, we have this search engine now that can find this document, but no, in reality, it's different. All the information is distributed over the internet. If you're lucky, you get a website on the Google Cloud or AWS where they list on each website, list all the offerings, list all the pricing, but it's still unlikely, right? But still then you have two different websites. So it's not possible to answer that query in a single document. And this is where we need multi-turn search. And this is something an agent can do. So for instance, what we would like also to have as a result is at AWS, we offer this NVIDIA H100 for $1.50 per hour. But as you can see, with this hybrid, even with this hybrid search, there's very few matching. You could say, okay, yeah, AWS is matching, and then this $1.50 could match to pricing in some semantic way. Yeah, the model could capture this, but it would downrank this a lot, because for the embedding model, this is actually very different. So this is like a definition of all the pricing and even Google Cloud and so on. And this document would just not match. But it's highly relevant for us, actually. And it should match. And all the other documents that also contain partial information to the final answer should also match. So we come up with the next paradigm. And a lot of companies doing this paradigm right now. There are like hundreds of solutions already with agentic search. So what it does is it collects not only one document, like doesn't retrieve only the first perfect document, or even not the top 10 for one search query, but it conducts multiple search queries and then takes a look at the top search results from all these different queries. So it first decomposes the user search query into partial search queries, gets a response, and then gives a combined response. And I will illustrate this in the following. So here is an overview of how this would look like. So in the top left corner, you see the user query. It's where do I get the cheapest GPU with 80 gigabyte VRAM? And yeah, when you type this into certain search engines, they might not come up with a result directly, because it will just give some hits on where this matches, 80 gigabyte GPU or something like this. So at first, the agent needs to generate some search queries, a list of smaller queries that are easier to understand by the search engine. And then after dividing this, so it can even generate like 100 of these search queries. And all are very different and lead to a bit of different results. For instance, it might use a search engine that doesn't work good with complete questions, but more with keywords. And then it would write NVIDIA H100 because it somehow knows that the H100 comes with an 80 gigabyte option and so on. And it creates ideally, it creates very creative, unique search queries that are not so much redundant. And then all these queries are fired against different search engines. This could be private personal search within the company, like from a company management system, something. It could be also a public search engine, like one of some listed here. For instance, Brave Search or even Gemini. You could consider the Gemini model with grounding as a search engine because you give it a prompt, what is this and that, and then it gives you an answer. And then after this, we retrieve all the search results. So agent gets all the search results for each of the query. And maybe it searched in multiple search engines at the same time. So you can assume it gets a lot of documents, complete documents, maybe also just snippets. So some search engines just provide a short answer format as a snippet. That would be ideal because of context length limitation. Okay, we get this as answer. And then the agent can decide, is this actually answering the question? Maybe in this process, it found out, oh, there are actually some more GPUs from AMD. They created now new GPUs. I didn't know about this. This must be something very recent. And in that process, found out about new GPU types and then can create new queries. And then this process repeats and repeats until the agent decides, generates the action final response. So, and then as you can see, this is some loop. So the loop is stopped and it outputs the final results based on all the information it gathered in the whole process. And some people might already have noted, you could go directly from here to the final response, even without searching. So what if the user, for instance, just says hi? Then you don't need to go into deep research of what this hi might mean. You can just respond directly also with hi. Or if it's asked, yeah, why is the sky blue? Then maybe the model knows already. Yeah, so this is the basic, very basic principle. So I also wrote the basic agentic search. This is the most simple one you could actually think of. Okay, maybe even reducing a bit of the search engines.
And we have a question if this can be used for academic research as well.
Yeah, this can also be used for academic research. So
it could be used for pretty much everything, right?
Yeah. So this can also be a research question. This is just the general concept, and then you can adjust it to the implementation of this. You can adjust to any domain.
And it's called agentic because the agent here, this robot icon, so it decides by itself whether to perform search at all, and if to perform search, what kind of queries to send and when to stop, right? That's why it's called agentic, because it can make decisions by its own.
That's why it's called agentic. And in this illustration, exactly this little robot, even I put it there, it's bothering me a lot because it gives like this magical component where people can understand everything that is around. But then this robot, what is it actually doing? What is this? What is this robot? And this is what I will clarify now. So what does actually everyone of this audience think? What is this?
So there is a bit of a delay between when we ask and when we answer. like 20 seconds. So, but please write in the live chat what do you think is the answer. But maybe while they are doing this, I remember in the demo that you gave a few weeks ago, we had a different example. So instead of the cheapest GPU, the example we had is running the Berlin Marathon, right?
Mhm.
So that was the query. But if we just do the keyword search, uh, it will still find some answers to this particular question, to this particular query, but it will not be the full list of things I want to know about running the Berlin Marathon, right?
Yeah.
Because there are things like, what was there? Preparation, recovery, other things, right? Do you remember what was there?
Yes, yeah, yeah. Like also even mental preparation, then what to eat before and so on. And maybe it's not really what you're looking for. Maybe it's like what training methods and so
Mhm.
on, what to use and where to run and so on. So one observation also in working with agents is that every user query is highly underspecified. It's just a small glimpse of the actual user intention. And so even for this query here with the cheapest GPU, you could think of what does the user actually want to do? Maybe they don't want to have like 80 gigabyte VRAM. Maybe they just want to train a certain model. And maybe I find a way that where the user can train this embedding model. So with much less VRAM by using certain library or something. So it's always yeah, really trying to find out the user intention. And I think agentic systems of the future, they will have much more humans in the loop, and it will. So so maybe you also tried out this agentic search or the deep search from Google and OpenAI and so on. So sometimes it's very useful, but sometimes it's like going completely in for me, like from my perspective, in the wrong direction, and then there's no way to interact in between with this system. It's just
Even, yeah.
20 minutes later you can
Mhm.
you can
Even
try
in
again.
this
Yeah.
query, even in this query, you don't know whether the user wants, like assuming that they just want this GPU, right?
Mhm.
Like we don't know if they want to train a particular model or not. Like even in this query alone, we don't know if they want to buy it or rent it, right?
Yeah. Yeah. That's
It's
also.
already, but then like even on deeper level, what do they actually want to do with this GPU? That's like the kind of next level question. And yeah, we already have answers to your question.
Mhm.
So it's an LLM model
Yeah.
and it's the chain of thoughts. So these are the questions we have. And also another question, this is the AI agent.
Yeah. Okay. Okay. Yeah. I think it's going very much in the right direction. So it is a prompt, an LLM, and a loop. So it's also code, right? There's also some Python code that is executing. Otherwise, just the LLM is doing nothing, it's just sitting there. So it's also a program that is written in some language, for instance, Python. And it's a large prompt that is processing something. So what is a prompt? And I would like to go with you through this whole prompt because that is actually everything you need to from terms of prompt engineering to create an agent. I know there's a lot of text, but as an outcome of this webinar, I think everyone should know how to program an agent. And this is really essential for this. So in the first part, we say you are a search agent that receives a list of previous search queries and their results. So let's go up again to this graphic. So it receives. So it's like stateless, right? This agent for now is the most basic form. It's stateless. We can assume. without making it too complicated. And what it has still is it has the list of all the search queries and search results. So in each loop, we store these search queries it made and the search results, and then give it this list. So it gets its states basically in the prompt, and then it knows okay, what did I look for already? What should I probably look on next, or is it enough to give the final response? So we give this to it, this list, and this list is the variable QA, question answer. So we tell it here is a list of questions and answers. So this is a list. It already made a question before or and gave an answer. And note that at the very beginning, this list is empty because it never made a question and never got an answer from the search engine. So, and we also tell it here is the user request, so that it keeps track on, okay, what was a user originally looking for? Because we don't do this and remind it every time this is what the user actually wanted to have, then it goes out of bounds. So we had like very weird things going on where it started here and ended up a totally different universe, basically. So we give these two data points, and then we tell it. So when responding, use JSON schema. Okay, we want to parse this response somehow, and then it should decide. So this is the agentic part here, because we force a decision. We force a decision from the language model, and it can decide, does it generate this JSON or does it generate this JSON here? So it can decide if it outputs mode is final, and then it gives the final answer here. That would be the complete list of all the cheap GPU offerings and everything. It could answer, in theory, it could answer right away. So it has no question answer pairs, and somehow the model is so intelligent and so knowledgeable and so up to date, it knows this information and provides a final answer right away. But what is more likely is that it thinks, yeah, probably, I don't know. So it conducts a series of search queries. So it generates this JSON with mode search. And then, yeah, okay, we instruct it to be more clear and nice JSON output and so on. But these three things are the essential parts. So we have the user request we always give. So this is give me the best 80 gigabyte GPUs. Then we have the previous question answer pairs. And we have the decision it should make between outputting two different JSON formats, choosing which one to output, either generating the final answer already given this information, or it generates the queries. And yeah, I told you it's an LLM. Yeah, we know all the LLMs. It's this prompt, but it's also an algorithm, because alone, nothing happens otherwise. And this is the most simple algorithm I came up with. And I know, like, algorithms discussing in presentation is usually not considered be so good, but I think there's no other way. I would like to empower you with really creating agents on your own. And I think the best way is through this code snippet here, and not through like graphics with errors going here and there. But this is something you can implement. I will go through the code quickly, but first want to say this is something you can implement for your specific domain, and then also adjust the prompt to your domain. So you would not say like you're a search agent, but you would say you're a search agent for medical documents, and you can adjust all the prompts. So this is like a starting point for you. So let's go quickly through this algorithm, or quickly, as long as we need, so that everyone understands. It gets a user query as input. So this is not surprising. This is a function. It gets a user query as input. And then also we can see there's only one return. It returns the final answer. So this is good already. This is the interface we expect. We give it some user query. It takes a while. There's a while loop. You can already see there's a loop. Processes something, and at some point it decides to return the final answer. So this is great. Then some things I didn't implement here because it's very specific to your specific domain. So it's an LLM call. It's just a function that calls the LLM. It gets a prompt and generates the answer. So you could use Gemini, OpenAI, Anthropic, whatever models you would like to use. You put instead of this function, or use this function as wrapper. It gets the prompt, creates the answer. Then this is your search engine. Can be a private search engine. It can be a MySQL database you have somewhere within your company. You have a search term and then find in a certain table certain documents. Can be semantic search, can be keyword search. This is also a very simple interface. Given a search term, getting a response, getting a list of response documents, getting something in string format back. And then this is the prompt we had above. This is the exact same prompt. This is that prompt we discussed before. And now we start with the algorithm. So as you have noticed already, there are these placeholders here. So we have the user request and the question answer. These are placeholders because it's a prompt template, actually. It's not a prompt, but a template that creates for each of these. When you put different variables, it's creating a new prompt where these placeholders are filled with values. And this is what we do here. We format our prompt. So we put the actual user query there and all the question answer pairs we gathered so far. And as you noted, it's initialized with an empty list. So we start with an empty list of question answer pairs. When you look at this prompt above, then it will just say, yeah, this is a user request with the 80 gigabyte GPU. And then here is a list of question answers, and this is just an empty list. But it's fine because we also told the model it can be empty. It can be empty. It won't be surprised. So we have our prompt. Based from this prompt template, we created our prompt and then just call the LLM. Might be Gemini, might be anything, might be any model. You have to do the implementation here for whatever model you want to use. And it will generate a JSON response. Okay, we load the JSON. Maybe you have to do even more depending on the model you use. Maybe it's not even able to create the JSON format. Maybe it has like some fencing around, like this triple backticks or so you have to remove. But this is just giving you the concept, the initial starting point. And for a lot of models, this will also just work. And then we have this condition where we decide how we proceed now. So it's getting this mode variable from the response JSON. When we go up to the prompt, then we see the generated JSON in both cases has this mode variable. So either it's set to final or it's set to search. And this is exactly what we check here. So if the mode is final, then we return the final answer directly. And that's it. So maybe the question was how many people roughly live on Earth, and it knows the answer already, and it will provide it here, just right here, even without looping multiple times. Or the mode is query, and then it falls back to here. And now we iterate through all the search queries it generated. Because just a quick reminder here, in the search mode, it generated also all the search queries. In a list, it can decide how long it is. You can also restrict it. You can write here a comment behind and say, yeah, at maximum like 10 queries. Because maybe also the queries are expensive you do to your search engine. So maybe you want to restrict it. And then it loops through all the queries. And for each query, it calls your search endpoint, whatever it is. Maybe it's an internal wiki or whatever, remote call, and you get the search results. And then for the first time, we added this QA variable. We add another question answer pair. So for each query, we add another question answer pair. And then the whole loop starts again. And this time it will actually see these question answer pairs. So yeah, if someone has questions already, then we can discuss them, because I think this is a base concept of agents, and it's very important for everyone to understand.
Yeah, I think the questions are related to how do we build upon this, and one of the questions is when should we consider using structured output and things like Pydantic for the final answer and search queries.
Yeah, you can also use structured output. So I really have no preference. I see it's like similar quality if you parse it yourself. Also, I think with structured outputs, this is good because it's the native way of doing it, and they probably optimize the model for the structured output. But usually you have to make a specific implementation for this language model to use their way of generating structured output. But with this prompt above, it's very generic. I can use almost any language model to generate this. And then
structured output only works for OpenAI and perhaps some other LLMs. I know this is one of the features in OpenAI, right? But like, let's say if we use, I don't know, whatever comes to mind, DeepSeek, right? Maybe we run it locally. It has no idea about this, right?
And then,
or maybe it does, but like some other model does not.
Yeah, absolutely. And then it becomes hard to benchmark when you have to do a custom implementation for all these language model providers. And yeah, for some you cannot even do. And I think this is fine. This brings you already quite far if you just prompt like this.
And another question is about function calling, but I'm not sure I know the concept. Do you know what is function calling in this context?
Yeah. So function calling became popular based on OpenAI release. They released this feature. It's called function calling, and it allows the developer to provide a function. For instance, like this, a search function, where you also use certain JSON format to describe my search function. It's like a different format, but I can describe it, and also describe all the parameters for this function and so on. So the language model gets the complete specification of this function. I tell it, yeah, please solve this task. And by the way, you have this function to find out about the weather. in any city. So as a parameter, you give me their city, and I will return the temperature there. And just by giving this to LLM and then asking it a question, then it can decide on its own, okay, should I respond to user directly, or should I call this function? It's then also not calling this function directly itself. It's then just outputting, like similar to this one, what I did here. It's just outputting a message, not agent or assistant, but it's out. So like OpenAI, you have all these messages one after another. You have the user message, and then you have assistant and user assistant, and then it outputs some tool use message, and then you still need this code around that is then actually making the call. So it's very similar to what we did here, but similar to structured output. It's more generic, more general, what I present you here, because you can use this with any language model and don't have to wait for maybe Anthropic or maybe other open source models to then also support function calling and support it in the exact right way. And you're more independent. Yeah.
So function calling and structured output is a convenient way to achieve what we want. Then we wouldn't need to program it ourselves, but then we're kind of limited to only the LLM providers that support these kind of things. So in this particular case, it's OpenAI that supports function calling and structured output, right?
Yeah, and I even think I would even say it's not even saving much work.
Okay, because like the code you have is fairly simple.
We have to write this code here anyways. Then it's not checking for is it final response, but it's checking is the next message that the model generated, was it a function call? Okay, yeah, then was not. Okay, then give final response. Otherwise, we call the function. So it's very similar. At the end, for this degree of customization that you can call any search engine and so on, you need this wrapping code always.
Another question is, how does the agent know if the info we get from the search engine is correct?
Yeah, good question. It doesn't.
It's like I imagine a situation when I ask how to run a marathon, and like I come across a Reddit post that says don't run, like or something like how mean people can be on Reddit. Like should the LLM consider this as gold standard data, or
it will. So
people assume it's good, right?
Yeah, so the language model has its own knowledge. And then for certain things, it will just say, wait a second, that's a lie. That's absolutely not correct. But for other things, and if it has less knowledge, then it will just see, okay, yeah, or agree. Yeah, this is okay, this is a source, and this is what the user wanted, and they want me to trust the source. Okay, then I generate this answer. But
you can explicitly instruct it, right? So
yeah,
you can don't use your own knowledge, use only the provided search results for making your decision, right? For example.
I wish it would be so easy. This is what I tried also, because it sounds very reasonable, right? But
yeah.
It somehow doesn't have this concept of what is my own knowledge, and so it
Mm-hmm.
will always bake in these biases and assumptions, and it was really hard. So this is like a whole different topic now. How we can, or extension of what we said already. So how can we create really good search terms? And there are non-biasing queries. For instance, even in this example with the GPUs, the query that comes up right away where it's saying, this NVIDIA H100 query, I think is too much of a bias already, because maybe this is not the best GPU for this. Maybe it should first ask for a list of all GPUs, first finding out, like removing this assumption of, oh, okay, I know already what provider provides us 80 gigabytes. No, it should maybe first even have to find out what is a GPU. Like you're really being really dumb, and then going from first principle to explore the knowledge of the database. Yeah.
Yeah, makes sense. But there is this, this simplest rack prompt that we have is if the answer is, if you don't see the answer to this user question in the provided list of documents, then say, I don't know, right? And usually it works.
Yeah. Yeah, usually this leads to infinite loops. As you
Yeah.
can see, this is very dangerous what I did here. So while true, and then who knows if it ever stops until my bank account is empty.
Yeah.
And we assign a budget. And then after the budget is used up, then we ask it, okay, but now you have to give some answer. Either you say like, okay, I really don't know, or you just don't include this type of whatever. And then it's also a good answer.
And budget could be anything like number of search queries we make, number of calls to LLM,
Yeah,
number of tokens.
Yeah, it could be anything. And we really assign money to this budget. So really think of, okay, user query should not cost too much.
Because we can easily, when we use OpenAI, I'm not sure about other providers, then we can we know how many input and output tokens we get, so then we can calculate the price, right? And then we can just know the cost of each query.
Exactly.
You know
And
how
then,
expensive it is on average to perform a query, one query like that?
or it could be something like, yeah, it depends very on the model. If you host yourself or so on.
Let's say GPT for O mini.
Yeah, it could be below 1 cent.
Okay.
So, yeah.
So fairly reasonable.
Yeah.
Okay. And another question is, why do we even need this loop? Can't we just do it in a single prompt?
Yeah, we can. And then it is called RAG, Retrieval Augmented Generation.
Okay. So in RAG, we always do search first, and then we feed it to an LLM, and then LLM summarizes the results.
But yeah, problem is it cannot really go so deep into. For instance, think of you give it the prompt, do a competitor analysis of these two companies. And in the language model, it doesn't even know what these two companies are. So in the first batch of queries, it has to find out about the company. What is it actually doing? What products is it offering? In what areas is it? Is it more in Europe, States, China? Where is it active? Because this all counts. It's important for a competitor analysis. And then after discovering the products, it should like really compare the product and find specific information about this product. This is nothing you can do in just one run. These are the limitations of RAG applications.
Have more slides? Do you have more slides? Because like if we continue with questions, we will.
Yes, yes, true. So yeah, context problem. What is even the context problem? So when we look at this graphic here again, then we see there's no problem. There's data flowing here and there and adding, and then we get final response. But when we really look at it, what does it mean? We make like 100 search queries here, and then generating for each of these search queries, maybe for multiple search engines, we get the top 10 results. and then put all of them into this one prompt where I showed you the placeholder. And then in every iteration, this is growing. So even though we have very capable models that support large context sizes, there are problems. So the cost explodes because it's more expensive to have the larger prompt. And then also it suffers from not relevant information being there. For prompt, it's always very, very important that you have a high density of relevant information. If you put additional information into the prompt that is not relevant, your result of this prompt, like your accuracy, the quality is really degenerating. So what we need actually here is some kind of filtering. So it should really be the first 3 or 10 search results. Should they really be here, or maybe they are not relevant, then we filter them out or only take part of this information. So for this, we start now. We have our single prompt that did everything, and now we start splitting it up. And each of these 4 boxes is one single prompt where we split up the prompt that does everything into single components. So user request comes in, and now we have a prompt that, just given the user request, decides what should be the next action. Should it be do a search, or should it be the answer? It doesn't write the final answer. It doesn't generate the search queries. That job is taken by another agent. So when I talk about different agents, it just means it's the same language model. It's just a different prompt. So people talk about multi-agent things and so on, multi-agent search engines, and the thing is, it's really just a different prompt, and at some point also different memory. We maybe can come later to this a bit, but yeah, this is like, I want to demystify all this agentic stuff. So then this prompt is just for the decision of what action to take. And in case it decides to generate the next queries, then it goes here, generate these queries, and then it triggers the prompt that is responsibility for generating the query and nothing else. So it gets here's a user request, and please now think about certain queries. And this allows you also to make this prompt much more sophisticated. You can give it more instruction, think from first principles, and use like the whole toolbox of other tools to make good search queries. So this is a whole research field on its own. That's why it's also good to pull these different components out of each other. Yeah, otherwise, also when you end up with a prompt that is really multiple pages long, where in a single prompt, then you have the problem that is LLM is just not able to follow all of these instructions at the same time anymore. So we have a bit more modular. And now when we run the search queries and retrieve the documents, there is another prompt that summarizes the output. It's not maybe only summarizing, but only filtering all the relevant information. And it can also say, yeah, there's nothing relevant in this document, not in this, not in this. And also know that this can also happen in parallel. So for all the documents that are retrieved, for each document, it asks, okay, given the user request, is there something useful in this response? Or given the user request and this generated query, actually. there's something useful, and then it provides a short answer. And then finally, here we have a much shorter prompt where not all the websites from all the answers are saved into a single prompt, but only question, answer, question, answer, question, answer. And this also adds up over time. Of course, if you have a couple of hundreds of this, then again, you're going to concern. But this is not something we cover today. This is where you would use some external or some knowledge, some long-term or memory you build up within this agentic search. So you would have like a database here, and then where you store all the question answer pairs, and then the decision process, maybe also multiple steps with different prompts where you first where you have an action of remembering something from the past, and then you can have access to your internal memory of the agent and retrieve information that is currently relevant for when it decides to give final answer. Or
It'd be like something like RAG on top of the knowledge
yes,
base.
exactly. This is like would be another internal rack where
So
it, yeah,
basically, we keep track of all the questions and answers we have seen over time. So we put them to some sort of database, Elasticsearch, MySQL, whatever, and
absolutely.
then we do a rack on top of this knowledge base.
Yes.
Cool.
Yes. But it's challenging also to not have redundant information there. So this is really it's really challenging. So, and I just want to show you how this summary prompt could look like. Also to demystify everything again. So here's a list of search engine results for the search query. Then it's a search query that was generated. And then here are all the search results. So it might be multiple pages of content, maybe HTML, or with our reader would be Markdown format. And then it also gives, again, this note here was the original user request, so it doesn't go out of bounds at some point. So this is like the whole context where this is happening, and then just generate the response and then JSON, and then the response is just 100 words maximum, and then giving a text response to this. This can also be much more complicated. So you could add here in the response also the citation, where it's coming from. You could add then also the link to the website, so that when later you present all these answers to the user, then you have all the references. You can click on them. You jump directly to the website, jump to where this was the citation came from, and so on. But again, we just for simplicity, we just show this. It could also be a list actually of citations. So this is more how we handle this in our Node Deep Research project. Okay, just I dumped a lot of other things, so there's a lot of things you can go from here. We don't have to cover this here. Just want to show you, we have this project called Node Deep Research, and initiated by our CEO, Han Qiao, Dr. Han Qiao. And yeah, this is basically covering what I told you, but much more complex, and thinking a lot of different cases that is over the time, fine-tuned and became much better. And it's pretty much on par with all the other deep research things. So, and this I won't cover, I think, because we run out of time. And I would like to...
by the way, this is so we spoke about this deep research. There is a demo that Florian gave It's in our channel in the open source spotlight section. So if you want to see this in action, check it out. Don't forget to give the project a star. It's an awesome project. Other projects too. Do you have time for one question?
Yeah, please.
This is a rather complicated question. So with RAG, we are still not sure how exactly to evaluate it. So what we end up doing typically with RAG, we evaluate search separately, right? Using search engine metrics or relevance metrics, things like, I don't know, NDCG, whatever. And then we use LLM as a judge, or maybe humans, to evaluate the quality of the answer, right? And this is important when we want to tune our model. When we want to try different LLMs or different retrieval methods, we want to understand how they perform. So we need a way to evaluate the whole system. How do we evaluate agentic search? What are the methods for that?
This is not easy. With just LLMs, you could think of question answer pairs when they are not there on the internet before your training time, then he just came up with these question answer pairs, and it could not know this. It just because it was very smart, so it came up with a solution. It didn't memorize just certain things. But here we did, for instance, certain evaluation, and then we also published our evaluation data set with this node deep research together. Published our benchmark, and now it's on the internet, and it can use the search engine, for instance, Google, just to find the answers, because it will go on its own GitHub repo and then find the answers there and then give the response. So this is difficult. Always needs to be some new questions.
Mhm.
And so there's also a bit of vibe testing, or just using it every day
Mhm.
to try to solve problems we have.
Yeah, so by using it every day, we collect enough data, then we record this data, and then we ourselves, as humans, as users, can label, can say, okay, this is a good answer, this answer is not good. So then we build the evaluation data set that we can later use somehow to, let's say we decide to go with model and see if it actually improves things.
So there are so many evaluation data sets. For instance, also Humanity Last Examen and so on. Well, we still do evaluation, and if it performs really bad, then it says something, because then it could have cheated but didn't, and without cheating, it didn't perform good. So this helps us still a lot.
Mhm.
So,
Okay.
like semi-decidable problem.
Mhm. Okay, thanks a lot. I know that wasn't a simple question, and keeping this for the end, maybe it wasn't fair, because this topic deserves a talk on its own. But thanks a lot, Florian, for joining us today, for giving a talk. Now I actually understand how to implement agentic search. To me, before it was just a buzzword. Now I actually understand what it means. What is behind this buzzword, how exactly we demystify this buzzword, and how do we implement this ourselves. So thanks a lot for doing that, and thanks everyone also for joining us today, for asking questions, for being active. It was an awesome session. Thanks everyone.
Cool, thank you.
And Florian, see you around. Since we both live in Berlin, who knows, maybe we'll just run into each other